Okay, the last part of electrical principles, and we're going to get to the infamous new question that nobody can answer. Why? I think I talked to you about this one last week.
Okay.
Changing the size of the conductor.
Oh, yeah, yeah.
Okay, so we'll talk about how RF affects components in circuits, and skin effect, and real and reactive power, and the electrical length of conductors. So reactive power is apparently wattless power. It dissipates no energy. You're just transferring energy back and forth in the reactive component. There's no energy dissipated. It just gets stored. Where real power is what's dissipated in resistive components. So the true power is going to be the current squared times the resistance, which is Watt's law. He didn't know about reactive components, I don't think. The apparent power is just going to be the product of the voltage and the current. Now, if it's purely resistive, you're going to get the same answer. If there's reactance in the circuit, the apparent power is going to be different than the real power. And the real power will be equal to the apparent power, which is what the power company does. They take your voltage times your current and multiply the power factor, which is really basically the tangent of the phase angle, I think, or the sine. What's it say? Cosine. And that will get you what the real power is. So we take the, right, because the cosine of 0 degrees is 1. So that would represent real resistive power. So once you start getting an angle greater than 0, then you've got the power factor correction. We'll have some examples. True power, like I said, is I squared R, or Watt's law, or E squared over R. Reactive power is, and I'm not sure why they use Q here, confusing. It's going to be I squared times X, or reactance, or E squared over X. And that's going to give you volt amps reactive. A lot of times I just shorten it to VA, or volt amps. You'll see the name tag on a lot of stuff, and it'll say so many, some number VA, because it's not purely resistive. If you look at UPSs, they'll give you a VA rating as opposed to a real power rating. So the apparent power is going to be I squared times the impedance, or E squared divided by the impedance. And that one they just do volt amps, because it's the composite. So if we have a sine wave, and the blue one is the voltage, and the red dotted line is the current, you see it's in phase. and the green is the power. So the power curve is positive above zero and follows the magnitude of the voltage. It doesn't change sign because it's real power. And the average power is going to be like a line right through there, or the RMS power. Okay?
Can you back up one slide for just a second?
This one?
Yes. All right.
Okay, so that's what real power looks like. No phase shift.
Why is the green line not the same wave shape as the other two lines?
It is.
No, the others start like that, and this one goes. See how it?
Well, it's the product. Maximum power is at the peak of voltage and current. It's going to give you your highest product.
Okay.
Minimum power is where they're both zero. So that's why the curve
But
looks
then,
like.
so at the very beginning,
Okay, it's zero and zero.
so wouldn't you think that the green line would go up like that instead of like that? It's supposed to be the.
That's the way math
product.
is. It is the product. But, you know, you're starting off with zero and very low numbers multiplied together. It's
All numbers.
and you're increasing as two sine waves, which are nonlinear.
Oh, okay. Wait a minute. I got it. You mentioned.
Okay. Okay, so reactive power is non-productive power or wattless power because the inductors and capacitors just store the energy and they return it back, except for a little bit of loss because they're not perfect. But in theory, they don't dissipate any power, so the net power dissipation is zero. So what is reactive power? Anybody for
I'm thinking, see.
Number D, D, what list?
Oh, yes. Okay. Yeah.
It's a lot of working.
doesn't produce any work
Okay.
because it doesn't move anything. What happens to reactive power in ideal inductors and capacitors?
It's stored, but no power is dissipated. It just sits there.
Right. To store the electric or magnetic energy. So here's a similar chart. Now we have reactance. So blue is still the voltage. And this is an inductor. So the current is lagging. And the power, okay, is going negative, an equal amount. So the average power is what? Zero. You're charging up the magnetic field, you're discharging the magnetic field.
What did you say about the average power? Zero.
Well, the green line is power, and this dotted line is zero. So I have an equal amount of power on the positive side to what I have on the negative side, so they cancel out. The average is going to be zero.
So that's pretty useless then?
That part of the power is pretty useless.
Okay. So what's all the numbers? Those are 60.
Well, we had zero resistance, and we had a reactance of 60 point something ohms.
Where did that
Uh,
was that?
because it was defined when whoever did this chart,
Oh, okay.
whatever inductor they used and whatever frequency it was at, which they didn't say, but you had basically 60 ohms of reactance
Okay.
and no resistance.
So it's straight down to the y-axis.
So what's the phase relationship between current and voltage for reactive power?
90 degrees on the awesome.
90 degrees out of phase. Okay, so in the real world, we usually have some resistance in there. We don't have a pure inductor or capacitor. So the real power is going to be the Watts formula, I squared R, and the apparent power is just the voltage times the current. And the apparent power will be higher than the real power by the power factor amount. So if in this example, we've got that 160 millihenry because it's got the same amount of reactance at 120 or at 60 hertz. So we've got essentially equal resistance and reactance. And we get an E over Z current of 1.41 amps. So our apparent power down here is 169 volt amps because we did I squared times the impedance. Remember, the impedance was 85 ohms. $60 over and 60 up, so the phase angle is 45 degrees. So your resultant vector was 85 ohms. So your apparent power is 169 volt amps. The reactive power, which is the vertical part of it, was 119 volt amps reactive. But the real true power was only 119.36.
$45.152 degrees.
If we plot the 60 plus J 60.3 and take the arctangent, remember how we calculate the phase angle? Okay, it's 45 degrees. Remember, they're essentially equal. So it's going to be approximately 45-degree triangle.
It would be exactly 45
if it was 60 even.
Yeah, exactly. It's approximately.
I guess they didn't want to figure out how many millihenries you need to get exactly 60. They had to go to nanohenries. So you got 119 watts of real power, but what you see as apparent power is almost 170. So the power company would be charging you for 170 watts, and you're only actually using 119. So here's another example of the voltage and current for that same kind of circuit and what power looked like. So you can see that the apparent power, which is the blue one, is higher than the real power, which is the gold or yellow one. And you notice the apparent power goes below zero. So that's the reactive part of it. So that cancels out the top part, which is the difference between the blue line and the yellow line, besides the phase difference. Question? Well, we'll do an example. How many watts are consumed? The circuit consisting of a 100 ohm resistor series with a 100 ohm inductive reactance drawing 1 ampere. Nice round numbers. So we're going to have another 45-degree phase angle. Everybody ready? 100 watts. That was a trick question. You didn't need to calculate anything. Because it has said how many watts, not volt amps or volt amps reactive. So the only watts were consumed in the resistor.
Good question.
A little tricky. Yeah, they do that.
Yes, they do.
Okay, conductors with alternating current and RF energy. A wire or conductor will have a small self-inductance. Just due to the length of it, you'll get a certain amount of inductance per centimeter, foot, however you calculate it. And when you pass a current through that conductor, you're going to generate a magnetic field around the conductor. Obviously, the higher the current going through, the stronger the magnetic field. And those magnetic field lines form a circle around the conductor perpendicular to the direction of the current flow or the charge flow. Here's a little example, and it's showing the magnetic field inside creating little eddy currents that occur on the outer edges, which is what causes the skin effect. And the higher the frequency, the more that effect has, and the smaller the skin, the less depth the skin effect has. At very high frequencies, the current travels only on the surface, basically. At DC, it travels through the entire conductor. At 60 hertz, you even see it, especially with high voltage, which is why they used to do a lot of aluminum or copper around a steel core, because it didn't matter what was in the middle, because the current was being carried on the outer part of the conductors, even at 60 hertz. And obviously as you increase the frequency, you get the thinner and thinner layer, so you get a smaller cross section of that tube, basically. There's a little chart here which I thought was helpful, but it's somewhat confusing. But it's showing at different frequencies what the skin depth is. So even at 60 hertz, it's 8 millimeters thick. So if you've got a conductor less than 8 millimeters, you're getting the whole thing. Bigger conductors, it's still going to be an 8 millimeter band on the outside. When you're up at 100 megahertz, it's 6 nanometers, pretty small. And that's what they call skin effect. And that formula is there, you can calculate it. It's not required, there's no question where you have to do that. But it takes into account the frequency, the resistivity, the permeability. And this is just another example showing what happens at DC, and as you go up in frequency, and this gets thinner and thinner. And as a result, the effective resistance increases. So that's why for high frequency stuff, you need conductors with large surface areas. Used to see it in old tube type transmitters, and they use not tape, but copper strip for off of the plate voltage to carry the current because of skin effect. Antennas at high frequencies tend to be tubular instead of solid because nothing in the middle matters.
Back to what you were saying about the tubes, and I've seen in commercial transmitters copper straps that are
Right.
almost a foot wide.
Yeah.
What would happen if you used a real narrow one instead of the big wide one? Would it get hot?
Yeah, because it had more resistance.
Okay.
And it would cut down on the current, you'd have an additional resistance in that path, which would cause a little more phase shift because now you got more R, so it's going to change the phase angle a little bit, which means when you neutralize it, it's going to be different. Sometimes they'll use tubes too. I mean, round tubes instead of flat. Let's see, what was this one about? This is an example for a 22 gauge wire at 100 megahertz. What the resistance is, it's an ohm. Although they didn't tell me what the length was, whether that's a centimeter or a foot or whatever. But relative, for a 10 gauge wire at 100 megahertz, it's 0.276. So whatever the length is, it's a lot less as you go to a much bigger wire. So what's the result of skin effect? Alpha sounds good to me.
Yep.
Here we go. As a conductor's diameter increases, what is the effect on its electrical length? I have no idea where this question came from. It seems to be in the section about skin effect. As far as I know, it has nothing to do with skin effect. I know what the answer is. I modeled it and proved it. I can't explain why that's the answer. I haven't found anybody that I've talked to that can. So this is one, if you get it, you just have to memorize the answer. Because I think it's just worded wrong. Because they say electrical length, and we normally talk about electrical length with velocity factor.
Yeah, I was going to say.
I don't know where skin effect comes in.
Is the velocity factor related to the resistance?
No. Velocity factor is affected by the impedance in the, well, like in coax, it has to do with the permeability in the dielectric,
Right.
but as far as I know, the resistance, the pure resistance, like in the center conductor or in the shield, doesn't affect it. And this is just talking about a conductor, not coax. So I modeled a dipole in EasyNet and changed the diameter by a factor of 100 just to see the effect. And it lowered resonant frequency, which means it increased the electrical length. I can't explain why or what the purpose of the question is.
D.
D. Most people say C.
That's what I would have guessed. Yeah, I would have just guessed D. I see.
So, like I said, anybody can submit a question, and if they accept it, it gets in the question. So we'll talk a little bit about capacitors at high frequencies. Basically, they store energy on the positive and negative increasing cycle. As the voltage goes up, you're increasing the electric field, so you're storing more energy. As the voltage goes down, you're decreasing the electric field, so that energy is coming back out somewhere. Oh yeah, this one. The more I looked at it, the more confused I got, so we're going to skip it. Because I don't remember where I got it, but it wasn't really showing what I thought it did. So what's the primary cause of loss in film capacitors at RF? Because in a capacitor, remember, it's essentially two plates separated by a dielectric. So at high frequency, you've got two conductors. And what happens at high frequency in a conductor? The current is carried on the surface. So it's going to appear more resistive. It's going to have more effective series resistance in that component at higher frequencies.
Skin effect.
Due to skin effect.
Let's try to get away.
Now, you also have what's called parasitic effects, both inductors and capacitors. In a capacitor, you can have parasitic inductance, where the leads, like you take a typical ceramic through-hole capacitor, it's got two metal leads on it. At high frequency, those are inductors in series with the capacitor. So there will be a frequency at which it's resonant. It's a series resonant circuit. And again, we have the resonance formula. So we call that self-resonance. You have the same effect we'll talk about next on an inductor, where you have parasitic capacitance between the windings. So it will be a parallel resonant circuit at a certain frequency. If we look at the impedance change versus frequency for that capacitor, you can see that the reactance is this dotted line for a perfect capacitor is going to go to 0 and then start increasing as a positive value. So we're actually going to go from looking capacitive to looking inductive. The effective series resistance is going to limit the lowest value of the impedance. because it's in series with it. So it can't be lower than what that effective series resistance is. So its reactance will decrease to the point where it's equal to the effective series resistance and then start increasing again with a phase change. So what parasitic characteristic causes electrolytic capacitors to be unsuitable for use at RF? Charlie? Yeah, I think they threw the electrolytic in to confuse you
That doesn't make a difference.
because it's the inductance of the leads. So inductors, well, we're storing our energy in a magnetic field, and as the current increases, the field increases. When the current decreases, the field decreases. So you have that coupled with the capacitor, and you're just going back and forth the energy in one and the other, which is why we call it a resonant circuit. So I have parasitic capacitance or interturn capacitance when I have an inductor, particularly one that's a coil, which has more than one turn or winding. And we call that self-resonance again. And the impedance in this case is going to be the effective series resistance plus the reciprocal of, because these are in parallel, the inductive reactance plus the capacitive reactance plus the internal resistance. So when you work that out, you can find out what, and you get a plot somewhat like the other one. The resonant frequency is still the same. It's going to be the effective capacitance and inductance. So you have to figure out what the parasitic capacitance is in order to find out what the resonant frequency is. Or you can measure the resonant frequency and then figure out what the parasitic capacitance is by going through the formula the other way.
You mentioned, if I can ask a question real fast, that that last formula on the last page was because it was in parallel. Did I hear that right?
Yes.
So the model right in the middle picture, the equivalent circuit on this page, the equivalent circuit you're dealing with now for an inductor, that you've got the equivalent parallel capacitance and parallel resistance. All those are in parallel when we're talking about inductors. But when you had the slide up a minute ago for capacitors, then the effective actions that we have there are actually acting like they're in series for capacitors?
Correct.
Okay.
Because it's a series LC circuit for a capacitor. You've got the inductance of the leads that are in series with the capacitor. And then you may have some parallel resistance, effective series resistance in parallel with the capacitor. But that starts getting it way too complicated for the questions on the exam.
Okay. Thank you.
So this is just a plot showing on a logarithmic scale the magnitude of the impedance versus frequency. And you see at resonant frequency, it's going to peak. And it starts off inductive and becomes capacitive, where the capacitor starts off capacitive and above resonance becomes inductive. Just remember that inductors and capacitors are basically inverses of one another. So what parasitic characteristic creates an inductor's self-resonance? skin effect is only contributing to the series resistance, which
Delta.
delta. What combines to create the self-resonance of a component?
Charlie.
Charlie. This one's kind of,
Yeah.
I could accept Charlie, but they like Bravo. I guess it's technically more correct because you have the nominal reactants and the parasitic reactants, and it's the combination of the.
The nominal is what you expect from an inductor. It would be regular inductance, and the parasitic in an inductor would be the parasitic capacitance, and vice versa for a capacitor. I think, is that the way they're going with it?
Yeah. Yes, he looks. Although I think you should get partial credit for inductance capacitance.
Makes sense
That's
either way.
not,
If you, yeah.
not a good one. Not my fault. Okay, so inductors at high frequencies. We have to look at, or inductance at high frequencies. We have to start looking at conductors themselves, because at very high frequencies, all conductors become inductors, even on printed circuit boards. So the inductive reactance is, again, the 2 pi f times the inductance. And the longer the conductor is, the higher the inductance, because it's a factor of length. It's a factor of permeability and the radius or the diameter. And you can use that formula down there to approximate it, where it's, I'm not sure where the factor 0.0002 came from, but you multiply that times the length, which is L in this case, times the natural log of 2 times the length divided by the radius. They're assuming a round conductor in this case. It's different for a flat one. And then they throw in the correction of minus 0.75, and you do all that and come out in microhenries. So you get microhenries per whatever unit of length that you put in the formula. So
I guess it doesn't make any difference what the unit is, as long as you say unit.
right. And you see the formula for a flat parallel, like you'd have a trace on a circuit board, is slightly different, more complicated, because you take into account the thickness of the copper, the width of it, and then they're also not including the capacitive effect with the dielectric of the circuit board and what's on the other side, which also, and this will have a self-resonant point also, which is something else beyond what we're doing. But at very high frequencies, you really have to consider all the traces as transmission lines and design them appropriately. And you can actually calculate how to make it a 50 ohm transmission line or whatever impedance you want. So why is it important to keep lead lengths short for components used in circuits for VHF and above?
Bravo.
Probably. Why are short connections used at microwave frequencies? Now, we didn't mention this specifically, but you should be able to figure it out. Because what happens if you have inductance and resistance? What does it change? The phase angle? And phase shift is important, like in modern radios where you're, SDR type, where you're using I and Q, which are 90 degrees out of phase, and you're transmitting those signals. So if you got additional phase shift going on in the conductors, you're no longer 90 degrees out of phase, so you can't cancel the sideband.
Yep.
Okay. So we talked about wattless reactive power. Eli the Iceman again. Skin effect. There's a good chance you won't get a question on skin effect, but there's a couple in there. Parasitic inductance and capacitance. The inductive reactance on conductors and phase shift in long conductors. So, actually, being 45 minutes late, we didn't do too bad.
Technical